Good day. Once again, thank you for attending today's focused remediation seminar. My name is Troy Leiser. I'm the Technical Director for Provectus Environmental Products. My presentation today is Advancement in Situ Chemical Oxidation with Continuous Reactive Oxygen Species Generation Technology. Brief outline of today's presentation. I'll give you an introduction to Provectus as an organization, and then we'll discuss the Provect-EBR technology and corresponding case study information. As was said before, if you have questions or comments during the presentation, please go to the questions tab in your GoToWebinar control panel, type those in, and we'll address those during the Q&A session at the conclusion of all of today's presentations. Quick background on Provectus. The company was formed and founded in 2014 through acquisition and utilization of patents on technologies for in situ chemical reduction, chemical oxidation, as well as methane inhibition. We've completed well over 2,000 soil and groundwater remediation projects, both here in the U.S. as well as internationally. Our backgrounds are in consulting, remediation design, injection and drilling, as well as the development of advanced remediation technologies. Provectus is a technology provider, not an implementation group. If your needs are for a turnkey design, Provectus would partner with implementation companies to provide you with that turnkey solution. So why the technology we're going to discuss today is important. The photo you see here is from an industrial demolition company located in my hometown here in Ohio. This earth mover sits out in front of their company, and as you can see there on the blade, it says you can't do today's job with yesterday's equipment if you want to be in business tomorrow. The photos you see there at the bottom are traditional equipment that we see utilized for our soil groundwater projects. Your geoprobe direct push rigs, the mixed trailers, our SVE systems. These are all equipment and technologies that we've deployed for the last several decades, and albeit very effective. So why would a new technology be needed? We're really looking to address some of the shortcomings of the chemical oxidation amendments, primarily the longevity of those amendments in the subsurface. When you look at the chemistries that generate the radicals or reactive oxygen species, we're greatly limited in the distribution of those amendments throughout the subsurface and the short reactive time of those species that we're generating. This requires us to have to continuously re-inject and introduce additional chemical into the subsurface. If we look to potentially design and implement a permeable reactive barrier, or a PRB, with a chemical oxidation technology. Normally for your PRBs, we're looking for these to be effective and reactive for several years. Anywhere from 3 to 5 years would be our goal. This is very difficult to achieve with traditional chemical oxidants. There have been some advancements when you look at like the wax impregnated amendments in the cylinders or candles that had been tried, and the utilization of potassium-based amendments with potassium persulfate or potassium permanganate. Owing to the reduced solubility of those chemistries, it allows you to extend their longevity in the subsurface, but normally only to several months. We can't really be able to achieve that multiple, somewhere 3 to 5 years, without having to continuously re-inject or reintroduce new chemistry into the subsurface. And, if we're going after chemistries that are not conducive to traditional PRB chemistries with the chemical reductants, and ZVI, things such as 1,4-D, MTBE, TBA, your perchlorate plumes, these we just can't, try to attack and treat reductively. If we're trying to establish these reactive zones in deep aquifers, if your contamination is 60, 80, 100 feet below surface, this would create a challenge for traditional oxidative chemistries. If we're dealing with difficult lithologies, those tight silts and clays, this will affect distribution of our amendment. These are things that we're looking to address with the technology we're going to discuss today. So when we look at the Provect-EBR system, what are we looking to do? What the system does, it allows us the generation of elemental oxygen and hydrogen peroxide, all in the presence of a ferrous iron release. The photos you see here are components of the Provect-EBR system. The photo on the lower right shows the downhole components. In the foreground, you see the EBR reactor. In the background of that photo, you see the sacrificial EBR electrode. The photo on the left shows you a portion of the control panel where everything is monitored and controlled. One of the very interesting and unique things with this system is the technology is monitored and maintained remotely through a partnership that Provectus has with the Field Data Solutions Group. We can generate and monitor real-time operational data from each one of the EBR system components. If adjustments need to be made, we can do that remotely from our computer station. This eliminates the need to have to deploy personnel out to a job site. The technology is patented both here in the US as well as in Europe by the Elgresi Group out of Netanya, Israel. Provectus has an exclusive agreement with the Elgresi Group to be the licensing arm to provide this technology here in North America as well as in Europe and in Southeast Asia. So how the EBR system works. If you've ever studied or familiar with an electrophenton's generator, there's some similarities here in such that the photo on the right, you see the EBR reactor in a tank of water. If you look closely, you can see an effervescent coming off of the reactor surfaces. On the catalytic surface of the EBR reactor, we're converting subsurface groundwater to elemental oxygen. And then on the cathodic surface, we go through a 2-electron reduction to convert that elemental oxygen to hydrogen peroxide. Again, that sacrificial iron electrode, we are passing a specific current density through that iron electrode, accelerating its corrosion and breakdown and release of ferrous iron particles. If you're familiar with the chemistry, when you have ferrous iron in contact with hydrogen peroxide, you generate the reactive oxygen species, the hydroxyl radicals, the superoxide radical, and hydroxyl radicals. Depending on our subsurface chemistry, we may also be generating ferrates, which would be your iron in the +4 to +6 valence state, which are also very, very reactive. On the lower right, you see a list of self-propagating reactions that continue to occur in the subsurface. The technology allows us for the generation and regeneration of these reactive oxygen species. This is what differs from an EF generator, where typically you're only going to be seeing generation of those reactive oxygen species directly in contact at that EF generation point. When you look at the EBR system, one of the unique parts of the technology is the generation of these iron +2, +3 nanoclusters. We're forming these oxyhydroxide particles of 2 nanometers or smaller from that sacrificial iron electrode. What this allows us to do as these reactions begin to form, we establish a thermodynamic differential and we generate this low-level Fermi wavefront. This creates a redox front generating truly radially from each of the EBR reactor electrode positions. This technology is not dependent upon groundwater movement or groundwater flux. This thermodynamic differential, obviously it flows from or moves from a position of the greater potential toward lesser potential. So we see a radial generation outward from each point. As we locate the EBR reactor electrode points throughout our treatment area, these redox fronts, as they emanate outward, begin to mesh together. Depending on the design of the implementation points, we're either looking to attack a specific area or form that barrier, as we discussed earlier, to create a truly PRB with this reactive redox front. So as we go through with our development with the Algresi group, we've recently gone through an improvement in that EBR reactive design when we looked at the materials that they're constructed from, as well as the mixed metal oxide coating present on each of those reactive plates. We've been able to improve this technology. We ran a study. The vessel you see here allows for, this is a closed system. It's about 200 liters in total, which would be, allows us to mimic the volume of water that we would see in a well 3 inches in diameter, in about 44 meters in height. So that's that same 200 liter volume. We were able to pull in a waste stream from an industrial waste treater within Israel, one of the Algresi clients, and test their waste stream and the efficacy of this new reactor design. And what you see here are the various contaminants that were present in this waste stream. We had BTEX components, petroleum hydrocarbons, as well as other non-halogenated VOCs. What we see here is the reductions in these various contaminants from our start time to a 96 hour. We saw up to 99 and 99.9% reduction in all of these various contaminant types within that 96-hour time period inside of that reaction vessel. So we know we're now being able to provide even a more reactive zone than the initial design of the system. When you look at the EBR technology, we can deploy this in one of two ways. We can have a fixed implementation. The photo you see there on the left is the EBR control panel deployed at an active fueling station where all of the components, that cement pad that it sits on, all of our wiring to our various reactor electrodes go out from there through a trench network to each of our EBR locations. The other thing we can do is deploy the system mobily. The photos there on the right, you see our EBR trailer. The photo at the bottom in the middle, you can see the control panel inside. This system would allow us to run, maintain, and control up to 10 reactor electrode sets. The photo there on the left was actually at the site that we have just concluded our most recent proof of concept testing. When we moved, we're actually have deployed our reactors and electrodes, and I'm actually on the phone there with my colleagues in Israel, going through a calibration phase to restart the system. I'm seeing things real time. That's the control panel for the EBR there that I'm working on. My colleagues in Israel are seeing the exact same information real time through that data connection, through cellular data grab, again with the Field Data Solutions Group platform. So we're both able to see this, get everything calibrated, and get the system started. The mobile design allows us to treat a larger area in sections. We can partition off a specific area, treat it, get that completed, extract our components, move the trailer, and redeploy to another portion of the site. So looking at the system and the project that we've just completed here in the Midwest, this was a benzene contamination site that we were targeting. This was a historic benzene release through loss of material from a transfer pipeline that had been utilized. Site lithology is a very tight natural clay. It's overlying a weathered bedrock on below it. Our contaminants here, our impacts were fairly shallow. We were typically dealing at about 9 to 15 feet below surface, which for a pipeline transfer should not be much of a surprise. Our groundwater here depths typically ranged anywhere from 5 to 10 feet below surface. We had very low hydraulic gradient here. There's pretty much zero movement of groundwater within this zone. When we looked at the site, we broke the site down into 2 pilot test areas. Area 1 was an unfractured area, so we've got natural native conditions. Just exactly what would be seen throughout our plume area. Area 2 was an area that had previously undergone hydraulic fracturing for potential use of a multi-phase extraction system. And we were trying to determine if the system, we would see a faster or greater effect in the fractured area versus the unfractured area. Benzene concentrations in this site are very, very high. Groundwater, we see anywhere from 300 to 800 milligrams per liter, or 300,000 to 800,000 micrograms per liter. Soil contamination, we're looking at anywhere from 400 to over 1,000 milligrams per kilogram. This release has been present for over 20 years. It was a historic release. Been there. Several other technologies have been attempted for treatment that have been ineffective, mainly based on these high contamination levels and the difficulty in the lithology that we're dealing with. So our objectives, obviously, would the Provect-EBR system be effective in addressing these high soil and groundwater contamination? And we wanted to compare the fractured zone versus the unfractured zone. If you've done any projects where you've done targeted hydraulic or targeted pneumatic fracturing, it's not inexpensive. There certainly is a cost associated with doing targeted fracturing work. We want to determine if the cost could be justified. And obviously we wanted to look at what our operational parameters were to determine what data are we acquiring? Are we acquiring the correct data and using that information to develop a full-scale alternative to treat this entire area? The plume here is actually 1 mile in length, not very wide, but its lateral distance is nearly a mile. And obviously, we need to compare, if the system is effective, how does it compare cost-wise to other available technologies? So again, here are the 2 pilot areas. Phase 1, that unfractured area on the left. The EBR systems were deployed in a box format. This would give us a look at if we were doing a layout to treat a specific area. Phase 2, in the fractured area, the EBR reactors were deployed linearly in a straight line. This would show us what effect we would have if we were deploying the system as a PRB. We had monitoring points. These are the GP points that you see here, as well as piezometer locations. These are 1-inch piezometer wells deployed throughout, where we could collect site groundwater data and determine, as the operation's progressing, how effective our operation is being. So the phase 1 in the unfractured area, again, you see the EBR points are listed as EBR U1 through U4, and we had 3 monitoring wells located within the perimeter of our EBR points, and we also had 2 wells located outside of the perimeter of our EBR points. The EBR reactors were deployed about 22 feet on center, and our monitoring wells were located approximately halfway between. Our piezometer points were located on about 5.5-foot intervals. So this allowed us, once the system was started, over time, we could see what amount of time was required to see positive effects at each one of those points. This gave us time and distance to see that radial impact, what we were able to generate as the reactive zone from each one of those EBR wells. Here you see again, in this area, our background benzene contamination levels were between 640,000 ppb and 850,000 ppb of benzene. Each one of these phases was run for 90 days. Again, this was a proof of concept. Can we have an impact on these contamination levels? Our goal was not to achieve complete area treatment. It was just proof that this would work. Here you see the reduction values at each one of these points at the conclusion of that 90-day operation. You see within the perimeter, our monitoring wells within the perimeter, we see 90% or greater reduction. The two monitoring wells outside the perimeter, we see anywhere from 50 to 60%. That shows us that we are able to generate a true radial front, reactive front from each one of those wells. Obviously, the ones within the perimeter saw better results as they're being influenced from more than just a single EBR reactor electrode pair. At the conclusion, 60 days after we shut down phase one, we went back and pulled soil samples from each of those. And at the specific depths that our reactor electrodes had been deployed, on average, our EBR wells were still showing about a 60% reduction from our baseline values. And you see the values at each one of our monitoring well locations, anywhere from 4% up to as high as almost 72%. When we go outside of that depth, you actually see an increase in that soil contamination over time. This is, we had generated and actually forced movement of that contamination across that zone due to that concentration gradient in being able to reduce that groundwater level so high. You see that flux, and we actually forced that rebound, which shows us had the system run longer, we would be able to continue to treat this and see those reductions across the board. Again, our goals here were not to achieve cleanup. This was proof of concept. When you move to phase two, then we go to that fractured area. The EBR reactors are deployed in a linear fashion. Here, we're again about 24 feet spacing on center. We have our various monitoring points and piezometer wells where we can pull samples to generate our data. Some of the results that we've seen, looking at that baseline, our ORPs in the area at our EBR wells, we were at about, slightly positive, about plus 88. Within those EBR wells, we're generating ORPs of almost a positive 700. This is a very reactive, very, very reactive wavefront that we're generating. So you see about a 600 millivolt increase in ORP within that zone. Contamination here in the phase two area wasn't as high, probably due to the fracturing that had previously been done, allowing for more movement of contaminant. But again, within our EBR wells, we saw almost a 98% elimination in that 90-day period. We see a 98% reduction. Our piezometer wells, again, we're at about almost 90% reduction there as well. Here's a graph of how that was laid out, and you see the reductions of that contaminant level at each one of those points. One of the interesting things here, we are able to monitor power draw during each one of the operations. What we were able to determine based on consumer electrical cost, it cost us anywhere from $4 to $12 per day to operate the entire system, which, if you're aware, much lower than like an SPE system. So our lessons learned, obviously the EBR system was successful in doing that. Our real-time monitoring, might be valuable. We did see some interferences there, so we were doing hand measurements. And again, that data we were able to pull from power draw showed that this is a very economical system to operate. We're addressing the fracturing versus unfractured, gathering that data to determine our full scale, which will be the right way to go. Appreciate everyone's attention for today's presentation. Again, if you have questions or comments, please type those in. We'll address those later on during the Q&A session. And with that, I turn things over. Thank you very much.